Alright, so in this video we go over section 12.1 sequences. So in this section we're going to look at how to find, we define sequences first and different kinds of sequences, and then how to find several terms of a sequence and how to define sequences in recursive form, and then move on a little bit into sequences to series, which is the summation of the elements in a sequence. So let's define what a sequence is. So you can always think of a sequence as a function whose domain is a set of positive integers, also called as natural numbers. Right? That is numbers that go from 1, 2, 3, 4, 5, no decimals, actually only integers, positive integers, from 1 to infinity if we will. So in this case, well, a finite sequence, it's going to be that kind of a sequence whose domain is a set of elements in this set, you know. It's 1, 2, 3, etc. all the way to n. There is a limit. That's why we call them finite, as opposed to infinite sequences in which the domain is all natural numbers. That is from 1 to infinity. Notice in this case we have a limit n, but in this case we have no limit. It can go all the way to infinity. Examples of sequences, of finite sequences, are like this one: 1, 2, 3, 4. Well, in this case it has a limit. The limit is 4. It's the fourth term. Well, this number by itself is just a number 2. Well, yeah, that's a sequence. Yes, I mean, even though it has one element, you can think of it as a sequence, if we will. This third example right here, 3, 6, 9, 12, 15. Well, that's another finite sequence because it finishes at 15. How do I identify a finite sequence from an infinite sequence? Well, in this case, we have a 1, 2, 3, 4 stopping at 4, and then we have this 1, 2, 3, 4, and then all these dots indicating that this sequence goes on forever. Same one right here, 3, 6, 9, 12, 15. Okay, it stops at 15, and then this one, 3, 6, 9, 12, 15, dot, 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 goes on forever. That's how we differentiate between finite and infinite. How do we write the first several terms of a sequence? Well, so we have this curly braces with the notation a sub n that indicates sequence. Well, this a can be changed to another letter, but that doesn't matter. And then on the right hand side of the equation, well, of the function or the sequence, we're going to have some expression or function that depends on n. All right, so yes, again, like I mentioned, a sub n is the one that is used to denote sequences. We also use b sub n, c sub n, or t sub n, and that's another very common to use as well. So over here, let's find the first 4 terms of each given sequence. Well, all we do is plug in numbers. So in this case, we're going to find a sub 1, actually a sub 1, and all we do for the first term, everywhere you see the letter n, substitute with 1. So that's 2 times 1 over 1 plus 3, and in this case is 2 times 1 is 2, 1 plus 3 is 4. This one can be simplified to 1/2. All right. Okay, let's keep moving on the next page to find the next term. So that's a sub 2. So all we do, I'm going to skip the curly braces. I'm just going to go with the expression. So 2 times 2 over 2 plus 3. So that's a 4 over 5. Well, this one cannot be simplified any further. We're done. A sub 3. Plug in 3 whatever you see the letter n. So 2 times 3 over 3 plus 3. And in this case, 6 over 6, which reduces to 1. Finally, a sub 4, because we're looking only for the first 4 terms. So that's 2 times 4 over 4 plus 3. That's an 8 over 7. that cannot be reduced. So in this case, the first 4 terms of the sequence are 1/2, 4/5, 1, and 8/7. Right? So in this case, it's a finite sequence because in this case, we're not indicating that we're going forever. They're only asking us for the first 4. Okay, let's look at another example. Some sequences can be defined in a strange way. I mean, it's not going to be just one expression, but more like if you will, like piecewise functions, and like in this case, n if n is odd and 1/n if n is even. So for example, a sub 1. So in this case, because the first term, the 1th term, if we will, the number 1 is an odd number, we're going to plug in 1 wherever we see n. So that's simply 1. A sub 2. That's, well, this 2 is an even number. We're going to use this part of the sequence. In this case, 1/n. That's 1/2. B sub 3, A sub 3. So 3, it's an odd number, so we use the n part. So that's plug in 3 to n. That's simply 3. And a sub 4, finally, that's 1/n because that's an even number, 1/4. So the sequence here is going to be 1, 1/2, 3, 1/4. All right, that's final answer. All right, let's look at letter C, B7, and this one factor right here, it will be very, very important to highlight. These factors are typically called alternating factors. These are alternating factors because here, depending on the parity of the exponent, this -1 may become a 1 or a -1, and that negative positive is going to make this sequence of numbers oscillate between positive and negative. Well, oscillate, that's more like alternate sign. All right, so let's see how about this one. So let's do B1. So in this case, -1 to the 1 plus 1 times 2/1. And in this case, what are we going to have? -1 to the 1 plus 1, which is -1 squared, times 2/1, which is 2. And then -1 squared. What's a -1 squared? That's a positive 1 times 2. That's equals to 2. B sub 2. That's a -1 to the 2 plus 1 over 2/2. Times 2/2. Okay, in this case, we're going to have -1 to the 3rd power times 1. 2/2 is 1. And in this case, well, -1 cubed, this -1 being raised to an odd power, that's going to turn into -1 times 1. That's, and in this case, a -1. B sub 3. -1 to the 3 plus 1, that's 2/3. So that's -1 to the 4th power times 2/3. And then in this case, -1 to the 4th power, that's going to be positive 1 times 2/3. That's 2/3. B sub 4. B sub 4, that's going to be, well, so that's -1 to the 4 plus 1 times 2 divided by n, which in this case is 4. These two 4s will be reduced to 1/2. And this -1 to the 4 plus 1, that's the same as saying -1 to the 5th power. -1 to the 5th power, that's a -1. That's an odd power times 1/2. And then that's a -1/2. And well, the elements of the sequence, let's list them. So that's going to be 2, -1, 2/3, and -1/2. As you can see, these terms have an alternation in the sign. positive, negative, positive, negative. All right, so that's why we call this alternating sequences, if we will. All right, let's see what's on the next page. Well, so one of the most important things to consider right here is that formulas that generate the terms of a sequence are not unique. Well, so we're going to look at that more in depth when you take calculus, when you work on shifting indices of series and sequences. So this is still yet to be known. So in the previous example, what we did is to actually give terms of a sequence given the general expression. So now, or the general formula. Now we're going to do this process backwards. So we're going to write a formula that represents the given sequence. And in this case, well, how are we? Here in this case, we need to think of ways to represent, or more to like identify a pattern. Notice in the numerators, we have the numbers going from 1 to 5, one at a time, with increments of 1. So we can actually call this a sub n. So that could be, well, notice for every time in the numerator, we have the denominator is 1 more than the numerator, 1 and then 2, 2 and then 3, 3 and then 4. So the denominator is 1 more than the numerator. So how can we represent that? Well, if the numerator is n, well then the denominator is n plus 1. Okay. And in this case, this if we start at for n greater than or equal to 1. Actually, n integer. Keep in mind that this is integers. Another way to express this, that's n and n minus 1, because if we look at the denominators, the numerators are 1 less than the denominator. But in this case, we want n to be greater than or equal to 2 in this case, right? So that's what we meant about getting the general terms of the sequences that may not unique, all right? But in this case, you need to be careful with the conditions. So in this case, n has to be greater than or equal to 1, and in this case, greater than or equal to 2. All right, so let's look at the next term, at the next example. For the next example, what do we have? Well, 1, 3, 5, 7. If we look at this sequence, we have a sequence of odd numbers. Well, be careful. How do we represent odd numbers? It's going to be one or the other. So 2n plus 1. Well, that's the general form of odd numbers. Plug in one number, multiply by 2, add 1. That's an odd number. However, in this case, it's not going to go like that if we start at n equals 1, because 1 times 2 is 2 plus 1 is 3, and it turns out that the first term is 1. So this is not going to help at all. Let's discard this one. What about 2n minus 1? Instead of adding 1, we can also subtract 1, and that's still going to give us an odd number. Plug in any integer, either odd or even, to 2n minus 1 or 2n plus 1. That's also going to give us an odd number. But in this case, if we start at 1, 1 times 2 is 2. 2 minus 1, that's going to give us indeed the first term of a sequence. So in this case, that's going to help. So let's represent it using sequence notation. So that's 2n minus 1. And that's final answer. All right. So we don't have to do two versions. With one, it's fine. Actually, if you want to just discard this one, that's fine. We're only looking for one in this case. All right, letter C. Oh, that's going to be an interesting one because number 1, it has alternating signs. Okay, it has alternating signs. Let's see what about this one. Well, so the numerator, well, in this case, what you might want to do is have this first term to be 1 over 1. All right. make it look like a fraction so we can easily see the pattern in this case. So a sub n, that's going to be, well, if you look at the numerators, the numerator is always 1. I'm going to leave some space here. Well, I'm going to write this -1 to some power. So it's not just going to be n. I'll show you why. And then, well, that's times 1 over, well, actually 1 over n, simply 1 over n, you know. But in this case, is it going to be n? Well, if I do a sub 1, -1 to the first power, it's going to give me a negative number. That'll be the first term. But it turns out that the first term is a positive number. So that's not going to work. I need to make sure that when I plug in a sub 1, the sign of that term is positive. So what we do is add 1. So a sub 1, 1 plus 1 is 2. Yes, that turns this -1 into a positive 1, giving us a positive term. And that's final answer here. Okay. That's final answer. Okay. So the factorial, well, what about the factorial? So that's like a special product, you know, when we have maybe you have seen numbers like this, like 4 factorial. That's not an excited number. It's an exclamation sign, but it's not an excited number. Well, that means what we do in this case is multiply 4 times all the integers below that number all the way to 1. Of course, we don't multiply by 0 because otherwise it's going to be 0 as final answer. We don't want that. So 4 times 3, which is 12. 12 times 2, that equals to 24. All right. So that's what the factorial symbol is. All right. Another way to define to actually write the terms of a sequence is by using recursive formulas, and in this case we write the following term of a sequence relying on previous terms, you know. So let's just do an example to show you what does that really mean. All right, so in this case we're given the first term S1, and we have this general term as S sub n times equals n times S subscript n minus 1. Be careful here. I'll try my best to make sure this is a subscript. You know, when we write this, we write it in a hurry, and we tend to write this as if we were multiplying, but it's not multiplication. So we already have the first term. They're asking us to find the first 5. We're given the first. Let's do the. Let's see. Do I have enough space in there? No. Let's do the let's do the remaining 4. So I'm going to do S2, and that's going to be, wherever I see the letter N, I'm going to plug in 2. So this is 2 times S2 minus 1. That's a subscript. And in this case, well, 2 minus 1, that's 2 times S1. But we know what S1 is. It's given previously. So that's what we mean by using preceding terms. We use a preceding term to find the preceding term. So in this case, what is S1? So S1 is 1. And 2 times 1 is 2. Okay. And then let's do S3. S3 is going to be 3 times S times 3 subscript 3 minus 1. 3 minus 1 is 2. But what is S2? Notice S2 is given from before. So we are going to use the preceding term to write that next term. 3 times 2 equals 6. S4, that's a 4 times S4 minus 1 subscript. That's 4S subscript 3 equals to, what is S3? That's given from before. So that's why we're using this recursion. We're using the preceding term to get the next one. 4 times 6, which equals 24. And last but not least, S subscript 5. That's a 5 times s 5 minus 1. And then in this case 5 s subscript 4, 5 times s4, which is 24. 5 times 24, that's 120. Alright? And that's final answer. Those are the first five. You know, that's the first one, second, third, fourth, and fifth. Alright, so let's see. Let's look at another example. The next example, it's kind of interesting because for this one we are given we're given the first two terms. So we need to compute only 3 more. And then the sequence, you know, the expression to get the remaining terms depends on 2 terms. So that is, well, in this case we already have u1, we already have u2. Let's find u3, which is going to be u3 minus 1 plus actually 3 minus 2, u3 minus 1, which in this case is u3 minus 2, which is 1, plus u3 minus 1, which is 2. And all we do is plug in 1 for u1 and 1 for u2. 1 plus 1 equals 2. Let's do s sub 4. I mean u4. u sub 4. So u4 minus 2 plus u4 minus 1. So 4 minus 2, that's u2 plus u3. And in this case, well, we know what u2 is, that's given, that's a 1. And u3, we got them from the previous step. That's a 2. And that 1 plus 2 equals to 3. u5, last of the sequence, u5 minus 2 plus u5 minus 1 equals to 5 minus 2, that's 3. 5 minus 1 equals 4. So in this case, u3, which was found a couple of steps before, that's 2, plus u4, which was found earlier, that in the previous step rather, 2 plus 3, which equals to 5. So those are the remaining terms, the 5 terms. So the first one, the second one, third, fourth, and fifth. Summation notation. Well, we're gonna move to something called series. Well, in the previous examples, all we did is make a list of the elements. 1, 1, 2. Well, let's actually write this in terms of a sequence. All right, and in this case, well, we didn't really do any operations with them. I mean, we just make a list of the numbers. But now we're going to do what we call summation notation. And when we add the terms of a sequence, that's what we call a series. Summation notation or sigma notation, we use the uppercase sigma symbol from the Greek alphabet to denote that we are adding. So the way we read in this case, well, this Greek letter, it's instructing us to sum the terms, and then the integer k is the index of the summation where the sum starts at, and then the n is going to be the upper limit of the summation, which is the stopping point. And a sub k will be some algebraic expression in which we will plug in numbers and such. Alright, so how do we read these expressions? Or, well, for example, sigma k equals to 1 to 5 of 5k plus 2. We read this, the sum of 5k plus 2 as k goes from 1 to 5. That's how we read one of this. So let's evaluate one of this. So in this case, the way we read this is the sum of 5k plus 2 as k goes from 1 to 4. So all we're going to do is, well, 5 times 1 plus 2 plus 5 times 2 plus 2 plus 5 times 3 plus 2 plus 5 times 4 plus 2. That is, we plug in all the numbers going from 1 to 4. 1, 2, 3, and 4. And all we do here is simplify this sum. Well, in this case, so that's a 5 plus 2, which is 7. 5 times 2, which is 10 plus 2, that's a 12. 5 times 3, which is 15 plus 2, that's a 17. And 5 times 4, which is 20 plus 2, equals to 22. And if we combine these numbers together, we should get a 58. All right. What about sums that have that don't have apparently, as well, the upper limit, or the stopping point is not a number, it's but another, simply another, another symbol. So what we do, so in this case, this is the sum. Well, this equal shouldn't be here. This is the sum of k factorial as k goes from 1 to n. That is, we're going to do 1 factorial plus 2 factorial plus 3 factorial plus 4 factorial plus 5 factorial. Well, we don't have time to list them all, so what we do in this case is plus dot 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 plus n factorial. And in this case, well, we basically kind of have a, well, it's not an infinite sum, it's a finite sum, but stopping at n, but we don't know what n is. So in this case, we don't have to bother and add all these numbers. So that's what we get here. Let's see what's next. So in the next, writing a sum using sigma notation. So that's the backwards of what we did here. So in this case, well, we have the sum. We need to write this using sigma notation. So in this case, this is the same as the sum of, well, let's see. Do we see a pattern? Well, for this pattern, what I see is that the numbers that go from 1, 2, 3, 4, and 5, it looks like the sequence or the general term starts at 1 and goes all the way to 5. And then notice all these terms have a power of 4. So in this case, I would say k to the 4th power, So k equals 1, k equals 2, k equals 3, k equals blah, 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 all the way to 5. What about this one? In this case, this one looks like one of those that do not have a limit, or the upper limit is n. So k starts at 1 again, and this is 2 to the k minus 1 under 1. Alright. Alright, so let's look at some, well, actually this title is wrong. That's actually properties of sums or properties of series. Well, so we're going to do some operations with series, and well, when we have the sum of some function times a constant, we multiply all the outputs by that constant. The sum of two expressions, it's the sum of the two sums. And same goes for the difference. The sum of the difference between two expressions is the difference of the two sums. All right. And then this one is going to be a little bit tricky. That's when we have because typically we work with sums that have a starting point at 1. But when we don't have a sum starting at 1, and we're going to do an example, we're going to use this property essentially, make it start at 1 and subtract whatever we left out. Well, whatever we leave out, but I mean, that's kind of a kind of weird to say. Well, actually, when we look at the example, that's going to make a lot more sense. Well, then we have a couple of definitions here. So the sum of the first, when we multiply, when 1 times a constant, all we do is multiply the n times the constant. The second property that has a very interesting and historical background. I'm gonna talk about that in a second. Essentially, the sum of the first n integers is found by simply multiplying n times n plus 1 over 2. And then the same for, we have a formula to find the first n perfect squares, n times n plus 1 plus 2n times 2n plus 1 over 6. You might wonder where this formula is coming from. Well, I'm going to show you how to get how this one was obtained. The other ones we don't need to do anything about it. And then the sum of the first perfect cubes, there's a formula which is there. There's actually a huge table to look for the sums of the perfect fourths and the perfect fifth and the perfect sixth, etc. It's a huge formula sheet. Well, what about this one? For example, the sum of all the first n integers. So you might have heard of a mathematician called Friedrich Gauss, or at least you have heard the last name Gauss, maybe in physics or something, in the electricity theory and electronics or electromagnetic fields and all that. So you might hear about this scientist, well, more like a mathematician. So when he was a kid, his father was an accountant, and when his father was doing his work, the little kid was always looking at mistakes his father was doing. And well, back in the day, in the 1700s, 1800s, well, it was not a father wouldn't accept from a kid that he was making a mistake. Of course, he as a punishment, for correcting the mistake, even though he was right, he was right about the mistake he was doing. His father didn't accept it, and as a punishment, he sent him to his room, and as an assignment, he asked him to add all the numbers from 1 to 100. Of course, the father thought he was gonna take a really good minute to find the sum. Imagine adding 1 plus 2 is 3 plus 3 is 6 plus 4 is 10 plus 5 15 plus 6 21 plus 7 20. Well, doing all that summation all the way from 1 to 100, well, that was not gonna be a really big task. So how did he do it? Actually, he went to his room, he did the summation, and he went back to his father with the final answer within seconds. How did he did it? Well, so this is what we are trying to do. 1 plus 2 plus 3 plus dot plus 99 plus 100. Okay, and let's call this S for sum. And then, well, let's call that S again, but let's do it backwards this time. Let's do it backwards. So instead of adding the numbers 1 plus 3 plus 1 plus 2 plus 3 plus blah 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 plus 100, you can add the same numbers in the reverse order. That's 100 plus 99 plus 98 plus dot plus 3 plus 2 plus 1. And then add this sum. Alright, so what is 1 plus 100? Isn't that 101? What is 99 plus 2? Isn't that 101? Alright, and then what is this 3 plus 98? Isn't that 101? What is that 98 plus 3? Isn't that again 101? What is 99 plus 2? Isn't that 101? And then what is 100 plus 1? Isn't that 101? Alright, so add these two and s plus s, isn't that a 2s? Right? Now, think of this 101 plus 101 plus 101 plus 101. Okay, so keep in mind that multiplication is no other than repeated addition. For example, 4 times 5 is the same as saying 4 plus 4 plus 4 plus 4 plus 4. So 1, 2, 3, 4, 5 times the 4, which equals to 20, right? Oops, I meant to show you this. 4 times 5 equals 4 plus 4 plus 4 plus 4 plus 4. And that equals 20. You know, so that's really... So this multiplication is, in a way, a shortcut to represent this repeated addition. So we can do the same here. This is not a 25, this is a 2s. So this 2s equals how many 101s do we have? Isn't that 101 times 100? Right? And then divide this by 2. Do not compute this yet. And then in this case, do you see a relationship between this and that? Isn't it the same as 100 times 100 plus 1 over 2? So this is how this formula came out over here. You know, so 100 times 101 over 2, that's the sum of the first 100 integers. And well, this little kid, I think he was 8 years old when he did this. Maybe not within seconds. It might have been maybe a minute or two, or maybe, I don't know, maybe yes, even seconds, but not just through 3 or 4 seconds. So this is what it was in his mind. And well, that's basically n times n plus 1 over 2, where n equals 100. And well, let's simplify this. That's a 50. 50 times 101. Let me get my calculator. I don't think I have it here. Yes. So that's 50 times 101. And that's 50-50. And of course, his father was so surprised that he got that sum like really, really quick. And of course, there might be other stories about the rest of the formula. Maybe they're not. I mean, it's not the purpose to prove them all or to show the origin of them all. But I think the one that is the most representative is the one that we want to. Then in this case, it's the sum of all integers. So for example, if you want to know what's the sum of the first 17 integers, well, multiply 17 by the next integer, which is 18, and then divide by 2. That's what's going to give you. The sum of the first 100 integers, 100 times 1 times 100 plus 1, which is 101, divide by 2, and that's the answer. All right, so let's move on to the examples on how can we apply this. Okay, because in this case, so look at this sum. Number 1, do you feel like plugging in 1, 1, 2, 2, 3, 3, etc. all the way to 24? We wouldn't have enough space in the paper here to do it that way. No, we wouldn't. And in this case, we're going to use the formulas from the previous page to actually, well, in a way of a shortcut, if you will. I mean, some of the calculations are going to be a little bit, they're going to take a while, but not that much. I can assure you that. But in this case, I mean, it's going to save, using those sums, those properties are going to save us from doing a lot of work. A lot of work. Okay, let me put them on the side, so I'm going to need them. So first of all, I'm going to use this properties first. You know, the sum and the difference. So we have the sum of a sum is the addition of the sums, and same for the differences. So this is what I'm going to do. I'm going to go the sum of k squared, as k goes from 1 to 24, plus, in this case, this is going to be a multiple constant, actually minus, not plus. K equals to 1 to 24, and K as K goes from 1 to 24, and for the last one, I'm going to leave the constant inside. I'm not going to pull it out of the sigma symbol. Alright, now I'm going to use the properties of sum. So the sum of the first n square perfect squares is going to be all this expression. So all this expression, that is n times n plus 1 times 2n plus 1 divided by 6. And well, in this case, I'm going to put this bar right here to indicate that this expression will be evaluated at n equals to 24. Minus 7 times the sum of the integers, which in this case is n times n plus 1 over 2. And in this case, I'm going to put the bar again to denote that n equals to, it's going to be evaluated at 24. What about this last one? Well, when we have some, in this case, maybe I should have added a number, another formula. So when we have a constant without some a sub k, k equals to 1 to n, all we do is multiply n times c. All right, so 24 times 2. So what are we going to do here? Well, plug in 24 times 24 plus 1 times 2 times 24 plus 1. The whole thing divided by 6. Minus 7 times 24 times 24 plus 1. And then 24 times 2, that's 48. Right, that's 48. Okay, let's see what are we going to get. Well, in this case, it's going to be a little bit messy, so you might want to simplify a little bit. 24 divided by 6, that's going to give us a 4 times 24 plus 1, 25. And over here, 24 times 2, that's 48. 48 plus 1, that's 49. Okay. Minus, okay, 7 over 2, nah, that's not going to happen. 24 plus 1, which is 25 over 2, that's not going to happen. But again, 24 over 2, that's going to be 12. So 7 times 12 times 24 plus 1, which is 25. And then plus 48. And if you put all this in the calculator, or if you want to do, to continue step by step, well, you can still do that. Or what you can do here is simply, again, put it in the graphing calculator. Let me see. Let me check my notes. What was the answer to this? 2848. And that's final answer. Alright, so let's have a look at letter B. So it's going to be a little bit similar to the one, but in this case, what's new, we're going to use the cubed, the sum of the perfect cubes. So in this case, I'm going to write this 4 as the coefficient in front of the sigma symbol, going from k equals to 1, k cubed. And then minus, in this case, 6. And then going to 10. And, from 1 to 10. So what are we going to have in this case? Well, we're going to look for the formula for the perfect cubes. In this case, it's the last of this table. Of course, again, this table is even bigger. I'm just giving you the basic ones. Well, actually, the one that I wrote here, it's here. Never mind. It's here. Cn. Okay. So in this case, for the cubes, so we do n times n plus 1 over 2. Very similar to the first n integers, but this one is squared. And then in this case, I'm going to put a bar to indicate that this one is being evaluated at n equals to 10. And then plus 10 times 6. We have the sum of some constant from k equals 1 to n. All we do is multiply n times c, or c times n, either way. Keep in mind, multiplication is commutative, so it doesn't matter. So 10 times 6, that's 60. So what are we going to have? Well, plug in 10 times 10 plus 1 plus 60. Okay, let's simplify this. Well, on the one hand, 10 divided by 2, that equals to 5, times 10 plus 1, I mean, that's 11. But this quantity gets squared plus 60. And in this case, if we simplify this, well, that's 55 squared plus 60, which using the calculator you should get 12,040. Final answer. Alright, so for examples A and B, notice the initial index starts at 1 for both of them. So now we're going to use the property that I mentioned before when our sum does not start at 1. It starts at 1 plus some number. Alright, so, and let me actually write that down here just so we don't lose, so I don't flip pages. So sigma going from k equals to j plus 1 to n, what we do is split the sum. Okay, let me just call it a sub k. That's k equals to 1 to n, which is what we want to obtain, but we subtract j going from k equals to 1 to j. Alright, so we're going to use this formula right here. Alright, so in this case, well, so you want to start your index at 1. So let's try to write a 1 in there. Alright, so let's try to write a 1. K equals to, in this case, something plus 1. What number plus 1 equals to 6? In this case, 5. So in this case, j equals to 5. Alright? That's what we are going to decompose this formula in. So that's 4k squared. And then we are going to subtract k equals to 1. Oh, wait a minute, that's equal to no, not subtracting yet. That's equals to k equals to 1, k equals to 1 to 10 and to 5. This 5 is going to go here. Both indices start at 1. One stop at n, the one that we want, and one stopped at 5. And in this case, 4k squared minus the same one. So what are we gonna do here? Well, let me take this out of the sigma notation in this case. Minus also 4. So what about the sum of perfect squares? Well, that's gonna be a big formula. N times n plus 1 to n plus 1 over 6. Alright, so on the one hand, wait a minute, this one goes all the way to 5, not 10. So on the one hand, oh, no more sigma notation, by the way. So this is, let me go over here. N times n plus 1 times 2n plus 1 over 6. But for the first case, well, that actually times 4 because of this 4. Evaluated at n equals to 10. And then minus 4n times n plus 1. The 4 comes from this coefficient. Don't lose track of that one. Over 6, but in this case evaluated at n equals to 5. So let's see what we get for this one. Hopefully have enough space for this. Yes, of course. Let me actually go up here. So in this case, I'm gonna substitute n equals to 10. So that's 4 times 10 times 10 plus 1 times 2 times 10 plus 1 over 6. Subtract 4 times 5. In this case, n equals 5. 5 plus 1. 2 times 5 plus 1. So let's do one at a time. So that equals 2. Okay, so let's see. 4 times 10 times 11. So that's 4 times 10 times 11 times 10 times 2, which is 20 plus 1. That's 21 over 6 minus 4 times 5 times 6 times times 2 times 5, which is 10 plus 1, that's 11 over 6. Alright, so let's see what we get. Well, in this case, 4 times 10 times 40. 40 times 11, that's 21. Well, let's use a calculator for this. Where is my calculator? It's right here. So, the first one, 4 times 10 times 11 times 21, and divide that by 6. That better be an integer. If you get a fraction for this one, double check. These are all integers, should be all integers. 1540 minus 4 times 5 will cancel these 6's. 4 times 5, that's 20. 20 times 11, that's 220. And then 1540 minus 220, 1320. And that's final answer. And this is a good place to quit, and this is the end of this section. I'll see you in the next video.